Today, class, we will be looking at section 3.3 and an introduction to transforming linear functions. As usual, this will be a 2-day lesson, so today we are just going to talk about shifting graphs left and right and up and down. So to start, I want you to look at this picture of these graphs, and you can see here in blue that Avery says that F and G, now notice that F is the blue one and G is the orange one. Avery says that F and G are the same, except every point on F has been shifted horizontally to make G. So remember, horizontally would be left. Okay? On the other hand, says they're the same, except every point on F has been shifted vertically to make G, which would mean up and down. So I want you to pause for a minute and take a second to see if you can support Avery's argument. And remember that did horizontally, and then also support Cindy's argument. Remember that Cindy said it was a vertical. So pause the video, think about it. Okay, so hopefully for both people, you said that the slopes are the same, so they have the same slant to them. But if we think about Avery's argument, we could take a point. So for example, over 1, 1, 2, 3, over up 1, 3. Okay. So the point on F that was 1, 3, you could say shifted 1 left because it became 0, 3. And you can see this was consistent throughout. So for example, if we looked at the point 0, 1, it shifted to the left to negative 1, 1. Okay, so you could in fact support Avery's argument. On the other side, if we think about Cindy's argument that it was a vertical shift, the easiest thing to look at for a vertical shift would be the y-intercept. So here we already said that it's a 0.01, and we could say that in fact for G that shifted up to 0, 3. So you could say it shifted up by 2. We could test this in another spot. For example, we could have taken this point that was at negative 1, 1, shifted it up, and you can see there's one on orange. Oh, sorry, this is at negative 1, negative 1. And this at negative 1, positive 1, and you can see we went up 2 as well. So again, both actually could be supported. So next we're going to talk about a definition. And this definition is a thing called a transformation. Okay? The transformation of a function, F maps each point of its graph to a new location. One type of transformation is a translation. Okay, so this whole section talks about transformations. We're going to start specifically by talking about translation. And a translation means you're going to shift the point on the graph the same distance. Okay, so it could be horizontal. So if you can take one graph and either shift it all up by the same amount, all down by the same amount, all left by the same amount, or all right by the same amount, that is called a translation. You can look at these two pictures, and this first picture says there's a vertical translation, because just like we talked about in the warm-up, this blue line, you could say was shifted up by 2, or I guess by 4, because it's counting by 4s in every spot. Okay, so the distance is the same. You can see that on the right side, we have a horizontal translation, so you can take any point and see that it shifts 1, 2, 3, 4 to the left. Okay, so I could take this point right here, and it was 1, 2, 3, 4 to the left, and that's consistent throughout the graph. Okay, so it's a translation when it is shifting a graph left, right, up, or down. We have a little bubble map to talk about the difference. And a transformation can be a reflection, rotation, dilation, or translation. You may want to pause the video after I get this slide up because this would be a good thing to write down. So transformations include all 4 of those things. No matter what type it is, though, it maps each point on the graph to a new location. But now you'll see our bubble map shows that this thing we're talking about today is called a translation. Again, it still maps each point onto the new location, but the key is it's sliding the points vertically or horizontally. Okay, so it's a subset of transformations, translations. So again, get that written down, and then the next thing I want you to write down is the essential question for today. What the essential question is, and what we're trying to figure out is how does modifying the input, which again is the x value, talked about that a couple days ago with domain range, or the output, y value, or the answer of a linear function rule transform its graph. All right, so obviously we need some examples to figure out what's going on here. So we're talking about two baby sea turtles moving towards the water after hatching. Byron, you can see the orange graph up here, starts 2 feet ahead of Frank. They move at the same speed to the water. What function represents each turtle's position? So as we reviewed, if we want to write a function, we're going to write in f of x equals mx plus b form. Sorry about that. I had to pause for a second. Hopefully the video kept going okay. So we were just saying that we can write the function in mx plus b form. And so since we're given 2 points for Byron, we can think about slope is the change in y's. So I'm going to find the slope. Change in y's, this could be y1, y2, and I can do 6 minus 5 over, this could be x1, x2, over 4 minus 3. 6 minus 5 is 1, 4 minus 3 is 1. So it's actually got a slope of 1. The other option would have been to just look at the graph and find a point, and another point, and then put one, to get to the next point. So that's the same option. Okay, and then we also know that b is the y-intercept, which is where it crosses the x-axis, or sorry, the y-axis, which in this case is 2. So a function to represent Byron's position is f of x equals 1x plus 2. Then if we look at Frank, we can look at the blue line. Again, we could do y2 minus y1 over x2 minus x1, or we can pick a point and do the rise of 1, run of 1. So we can see that the slope for Frank is also 1. The y-intercept in this case, it does actually cross at 0, 0, so it's 0. So I can write his equation as f of x equals 1x plus 0. Now you wouldn't actually have to show the plus 0, but what we can see is that they have the same slopes, but the y-intercept is 2 higher. So when we add 2 instead of 0, we can then conclude that it is a vertical shift of 2. And if we pick any point along the graph, we can see that the constant of 2 shifted it up by 2. Okay, so now we're going to look at a second example, and this one we have to fill in the table. So it says, how does adding a constant to the input, which is the x value, affect a linear function? Okay, input is the same as the x. So we're talking about f of x is 2x minus 4, and g of x, you can see, is 2 times x plus 5 minus 4. You can see the difference is that we're adding 5 to the x, and that's why it's adding to the input. Okay, so if I plug negative 2 in for 2, I would do 2 times negative 2 minus 4 gives me negative 4 minus 4, I get negative 8. Okay, in the second column, when it says to take x plus 5, they're literally just saying the negative 2 that they're saying x is, plus 5, so that one's 3. And finally, for g of x, they're saying, okay, do 2 times the x, which is negative 2 plus 5, minus 4. This would give me 2 times negative 2 plus 5 is 3, order of operations, minus 4, 6 minus 4, and I get 2. Okay. So why don't you pause the video and take a minute to do like another row or two, and then you can check the video to get the rest of the boxes. So hopefully you went through and practiced your math, and you should have gotten, when x is negative 1, you should have gotten negative 6, 4, and 4. When x is 0, you should have gotten negative 4, 5, and 6. When x is 1, you should have gotten negative 2, 6, and 8. When x was 2, you should have gotten 0, 7, and 10. For 3, we got 2, 8, and 12. And finally, for 4, we got 4, 9, and 14. So this is all well and good. But now let's go ahead and graph these two lines. Okay, so now that we have a bunch of ordered pairs, when I go to the next slide, you'll see that the table is the same. Without the x plus 5 column. But if we graph these, okay, I can either take ordered pairs. So I like 0 ordered pairs. So for this, I'm going to take 0, negative 4, plot a point, and then I'm actually going to use this 1. I'm going to go over 1, down 2. This is going to be for f of x. I need 2 points to draw a line. Draw a line through those points. I'm going to switch colors now. And I'm going to graph 0, 6 for g of x. It's way up there. So I'm actually going to go negative 1, 4 because I ran out of room. I'm going to do one more just because that one kind of went off. I'll go negative 2, 2. So again, the light blue is going to be my g of x. And then we're going to talk about how these compare. Okay, so we could talk about the vertical shift, just like we did in the warm-up, where you can talk about it vertically or horizontally. But instead, let's talk about a horizontal shift. So I can see this point right here is at negative 2, 2. And this point looks like it's at 1, 2, 3. If I look at that, it looks like I shifted 1, 2, 3, 4, 5 to the left. Okay, I could test another one. 1, 2, 3, 4. Negative 4, negative 2. This one was at 1, negative 2. 1, 2, 3, 4, 5. Again, I went 5 left. Now, if you recall, the change we made is that we added 5 to the input. And adding 5 to the input actually shifted it 5 to the left. So what we can conclude from this example, and you'll want to write this down, is that adding a constant k, so any number to the input or the x value of the function, translates the graph horizontally. So horizontally, units. But remember, it's the opposite of what you would think. When we added 5, it actually shifted to the left side. Opposite way you would think. So if it's a minus, it shifts it right. And if you add, it's going to shift it left, like it did in our example. Okay, I'm going to stop this video. This is going to be part 1. And then I'm going to do another video that you're going to want to talk about shifting vertically. So go ahead and find the next video for this lesson.